In this video, we are going to derive the equation for a parabola. And I do want to say this is for a simple parabola which has a horizontal directrix or a vertical directrix. Now to begin, recall that a parabola is the set of points, so all ordered pairs in the Cartesian plane, which have the same distance from both the focus as from the directrix. The focus is a point, remember, in this particular picture with this smiley face parabola, the focus is above the parabola and the directrix lies below, and you can think of these as magnets. So every point here, if I walk from a point x comma y, it should be the same distance to walk to the red point called the focus as it is to walk straight down, that would be the shortest path, to the directrix, the horizontal line below it. Remember that we call this point on the base of that parabola the vertex. So the three keywords, vertex, focus, and directrix, we'll be working with those. Now, the vertex, remember, is often denoted as h comma k. That's a typical representation for the vertex. Now you might see something else out there, but typically h comma k, and that's what I'll be using in these slides. The directrix, since that in this form is positioned below the parabola, it is p units away from the vertex. So I have used the same k value on the vertex, the y value, and I've subtracted some so that the directrix is a horizontal line, y equals a number, in this case y equals k minus p. The focus, which is lying above the vertex, is a point, h comma k plus a little bit, so k plus p. Now p is going to be our distance. It's simple right here. From the vertex, this value would be p to go above and below, but we want p here to just represent a constant that could work for any point on the parabola, and so that's why we use all of these letters. We want an equation that works for every point on the parabola. So p will be that value that helps us find our directrix and focus. Now, from this class we worked with the distance formula. We know how to find the distance between 2 points. So my next statement, then the distance from any ordered pair on the parabola to the focus, which recall is the point h comma k plus p, must be the same as the distance from any point on the parabola x comma y to the directrix. I encourage you to pause the video and try to think about how to do this yourself. Don't let me rush you through this. Draw a picture and think about the distance formula, the distance between 2 points. How do we represent that? You'll do this for the red case and this blue distance as well. You know that those must be the same, so you can set them equal to each other. After I spent some time with this is what I have. So the distance from x comma y to the focus, you'll notice I took the difference between the x values here, and I took the difference between the y values. I plugged those into the distance formula, and I get a term, an expression that looks something like this. Now the distance to the directrix, to be honest, you don't need the square root and squaring that. It is just a vertical distance. Since you will be going from a point x comma y straight down, the x values would be the same. Since that path is straight down, your x values won't matter. It's simply a vertical distance, so you'll just have the difference between the y values, y minus the y value on the directrix, which is the quantity k minus p. You might be asking, well, why did you leave the square root on? I actually have a reason. Since both of these are squared, I know that the distances must be equal to each other. Since both of these are squared, I can square both sides, or since both of these have the square root, I can square both sides to eliminate the square root on the left-hand side. And so that's the reason that I went ahead and did that. We are going to try to simplify this down. So you'll notice on this slide, I've already canceled the square roots on both sides. And I want to break this down a bit. So what we're going to do is expand both sides. When we expand both sides, some nice things actually cancel here. From the distance formula, I did cancel the square roots on both sides. And then you'll notice that I also distributed the negative inside. So y minus k minus p will be this expression when I lose those two parentheses. Over here I'll have y minus k plus p. You'll notice that's what I have named equation 1. The next thing I'm going to do might seem strange. The reason I'm going to be doing it is because, two reasons. I know what I'm looking for because I'm a little bit experienced with this, and I realize that that can make this next step uncomfortable if you haven't worked with this before. Another thing is I just know it's going to be a nice trick, and it's going to eliminate some steps. You don't have to do what I do. You can do this other ways. It will require a few more steps, but if you want to pause the video and work it yourself, what you'll need to do is expand this term right here. I think that a lot of students would want to expand this as well. I'm going to suggest that you don't. It will be extra work, and again, it's my experience that allows me to know that you won't need to expand this, but this part right here and this part right here, I do want to expand those. How I'm going to do this is use some new parentheses. These parentheses didn't do anything to change it. I grouped around y minus k on both of these. Parentheses didn't change that in any way, but the reason I'm doing that is as a teacher, I want you to notice that this is a binomial squared. So a term right here, minus b, you have two terms. I'm going to consider these as two terms squared, and here something plus something squared, a binomial squared again. I'm going to expand that. We've talked about that in this course. Again, I'm just leaving the x minus h quantity squared alone. Here's your first term squared minus 2 times your first times p plus p squared. Here I have your first term squared, 2 first term, second term, product here, plus p squared. So please pause the video if that doesn't make sense. I'm simply using some algebra concepts that we've practiced in class to expand that second line. Once you do that, you should notice that you have some common expressions on both sides. We are going to combine common terms. Because you have a y minus k quantity squared on both the left and right, you can subtract that from both sides and it cancels. P squared is also on both the left and right hand side, so those also cancel. So you'll notice really all that's important, these extra terms here, you should have an equation that looks something like this, labeled as I have labeled equation 2. Now, hopefully you'll also notice 2p times the quantity y minus k, I can group those together so that I'll add this to the other side. So add 2p times the quantity y minus k to both sides, and I end up with this equation. This is what needs to go in your notebook. I have x minus h quantity squared is equal to 4p times y minus k, the quantity y minus k. This is a very common form for a parabola, but I don't want to confuse you. Depending on the textbook or the teacher or the online tool that you're using, you might also see it in this form. You'll notice these are the exact same thing. 4p is simply divided on both sides so that it's out front of the squared term. This would be your leading coefficient a that we used when we studied quadratics, ax squared plus bx plus c. You can use either one of these. Be flexible with this. Don't misunderstand, they're not different equations, they're the same equation, and they will both give you the necessary information. What we will be practicing is rewriting quadratics in one of these forms so that we can find h and k as well as p. Now remember, h comma k is the vertex, p is that distance from the vertex to the focus or from the vertex to the directrix. Now after this work, we have found the equation for a parabola, so that you might want to have this in your notebook, and I've summarized some of those notes here. So the focus was a point, the directrix was a horizontal line, and the vertex is always h comma k. These equations are the exact same. Now we only derived the equation for a horizontal directrix. You could again go through this process for a vertical directrix. So what I mean by that is, let's say that you didn't have a function, you had a quadratic of y. So y was squared, but x was linear. This is not a function, y is not to the first degree, but we can certainly do this process again, and you will get a formula that looks quite similar. You'll notice that where we had an x minus h, we now have y minus k. Where we had y minus k, we have x minus h, and so that's what we'll switch on these, again because they're showing you transformations. In this picture you have a smiley face parabola. You could of course have a downward facing parabola if p were negative. So if p is negative, that's going to make this term negative, which would give it a negative leading coefficient, and the parabola will turn upside down. Still will be a function because y is linear, but it will be upside down. It will be a frown. Here, if the focus, if this parabola instead turns the other direction, if the focus is inside that parabola and the parabola faces to the left, then you will have a negative p. So that is why these formulas do work for all cases. It's simply that I only did the two pictures are just summarizing the two cases here as such. Best of luck. You're not going to practice a few exercises. You will be finding H, K, and P.